Finding the critical numbers, you know, first means find where the derivative equals 0 or doesn't exist. So this one for sure is just going to have where the derivative equals 0, because you know that this always exists. So if I set this equal to 0, I get sine of x is negative 1/2. So I'm just looking between 0 and 2 pi. So that means I'm looking at 7 pi over 6 and 11 pi over 6. So now, to find out the intervals where the function is increasing and decreasing, I want to either graph the function, right, the derivative. I can either graph that, or I could do a sign chart. So I'm going to do both. So if I graph this, f prime, and you get to choose. There's no one way. So 2 sine and shift it up 1. You know sine starts here, and so it would come up and then down like that. Okay. You know that the x-intercepts will be the 2 critical numbers, right? So then I can take a look and say, okay, if I'm looking at the critical number of 7 pi over 6, that would be this one. I see that y, I just look, hold on. I just want to find out where it's increasing and decreasing. Sorry about that, I'm jumping ahead. So this is 7 pi over 6, and this is 11 pi over 6. So I can see the function is increasing when the derivative graph is above the x-axis. So on this interval, it would be from 0 to 7 pi over 6, and then from 11 pi over 6, and I'll just say to 2 pi. That's where the derivative is positive, so the function is increasing, right? F of x increasing, and that's when the derivative is bigger than 0. Okay, so if we're looking at below the x-axis, that's this area here. So from 7 pi over 6 to 11 pi over 6, that's when the function is decreasing because the derivative is less than 0. All right, now we can either use a sign chart or look at the graph of this derivative. So do both ways. So first off, if I'm looking at the critical number, x equals 7 pi over 6, before 7 pi over 6, I see the derivative graph is positive. After 7 pi over 6, I see the derivative graph is negative. So if I say y prime changes from positive to negative, therefore I know that that point must be a local maximum. Hold on, I gotta fix my fan. Freaking out. It's making an annoying amount of noise. Okay, so now let's go to the other critical number, 11 pi over 6. So I see that before 11 pi over 6, it's negative. After 11 pi over 6, it's positive. So I see that y prime changes from negative to positive. So therefore, f of 11 pi over 6 has got to be a local minimum. So it's going down and then it's coming up. Okay, so if instead you wanted to do a sign chart, what you would do is you just make an x-axis here, 7 pi over 6 and 11 pi over 6. So it's the critical numbers that you put here, right? Critical numbers there. Then you check numbers in between into the derivative. So let me just write the derivative here. So we have it accessible. So it's 1 plus 2 sine the x. So I'm going to pick a number before 7 pi over 6, and it doesn't matter what number. I'm going to choose pi. So if I choose pi and put pi, let me move this up a bit, and put pi into the derivative, sine of pi you know is 0, so that gives me 1, so that's a positive number. And then I'm going to choose another number in between these two. So if I choose 3 pi over 2, f prime of 3 pi over 2, you know sine of 3 pi over 2 is negative 1. So 1 minus 2, that's a negative 1. So that's a negative number. Oops, did I write negative? No, it's positive. Positive here, negative here. And then here I can choose 2 pi. And so if I put 2 pi into the derivative, right, I get 1. So it's positive. So we get the same result before and after 7 pi over 6. The derivative changes from positive to negative. And then before and after 11 pi over 6, the derivative changes from negative to positive. So however you want to go about it, you can get the same result. Okay, let's go back to these antiderivatives from section 1. Antiderivatives are really important. Really important, and they're hard. So let's make sure we're always taking the time. So remember in the beginning days of taking the derivative with the power rule, you had to get x to the n, right? And so I'm going to make a parallel here. When you take the derivative, you had to get x to the n. So then you could say the derivative was x to the n minus 1. Okay, so if I have a function that's x to the n, and if I want to find the antiderivative, it's x to the n plus 1 over n plus 1. Okay, so let's take the time to rewrite this. So f prime, so this is like the number 3/2 times 1 over x. This is like the number 2/3, and I'm going to rewrite this as x to the negative 2. And then minus 3/2 x. So it's an easy thing to do, but it's a hard thing to remember that the antiderivative, let me write this down, if f of x is 1 over x, then the antiderivative is ln of the absolute value of x. So that's this one. So you have to always be on the lookout for it. So if I take the antiderivative, to get f of x, I'd carry along the 3/2. This antiderivative gives me ln, and it's important that you put the absolute value bars there. Then I'm going to carry along the negative 2/3, and then if I take the antiderivative of this, remember I'm doing this rule, add 1 to the exponent and put it over that number. And then if I move on to this one, I'd have a minus, let me fix that. I'd have a minus 3/2 x squared over 2, and then I would put in the plus c, because that's the most general antiderivative. They don't give me information to solve for c here, right? And that's a fine answer, or you could fix it up a little bit, right? So you could say that your f of x was equal to 3/2 ln of absolute value of x. These two negatives make a positive 2/3, and sometimes it's nice to write the negative exponent in the denominator, and this would give me negative 3/4 x squared plus c.